Right now, somewhere in the universe, two black holes just collided. Not in the past, not a million years ago. Right now, as you're watching this video, as you're breathing, two objects each heavier than our entire sun are crashing into each other at a fraction of the speed of light. The collision releases more energy in a fraction of a second than our sun will produce in its entire 10 billion year lifetime. Space itself tears open. A ripple, a shock wave through the very fabric of reality, races outward at the speed of light in every direction. And we can feel it. Here on Earth, in a pair of L-shaped tunnels buried in the ground, lasers are bouncing back and forth between mirrors so precisely polished that a single human hair would be a mountain compared to their surface. When that ripple from that black hole collision reaches us, those mirrors move. Not much, less than 1,000th the diameter of a single proton. But the instruments catch it. They always catch it. In May 2026, the LIGO, Virgo, and Kagra collaboration, 3 gravitational wave detectors spread across the United States, Italy, and Japan, published the most extraordinary catalog in the history of astronomy. In just 9 months, from April 2024 to January 2025, they detected 161 brand new black hole collisions. 161. That brings the total number of confirmed gravitational wave events to 390. Events that would have been completely invisible to humanity just 11 years ago. But the number is not the shocking part. Inside this catalog are black holes that should not exist. Black holes sitting in a mass range that our physics has called forbidden for 60 years. Mass range where stars aren't supposed to leave anything behind when they die. And yet, there they are. Detected, confirmed, sitting inside the forbidden zone and completely defying the rules we thought governed how black holes are born. Something is going on in the universe that we do not fully understand. And what scientists found inside catalog number 5 may force us to rewrite the physics of how the most powerful objects in existence actually come to be. Stay with me, because this gets stranger. To understand why these black holes are impossible, you need to understand what is supposed to happen when a massive star dies. When a star runs out of fuel, gravity wins. The core collapses. If the star is big enough, the collapse is so violent that it triggers a supernova explosion, one of the most energetic events in the known universe. What gets left behind depends on how massive the original star was. A star around 8 to 20 times the mass of our sun leaves a neutron star. A dense ball of neutrons the size of a city, but with the mass of a star. If the original star was heavier than around 20 solar masses, the collapse is too powerful, even for neutron pressure to stop it. And what's left is a black hole. This has been our model for decades. Massive star collapses, leaves black hole, bigger star, bigger black hole. Linear, predictable, logical. But there is a problem. A problem that astrophysicists predicted in the 1960s, published papers about, argued over, and then largely set aside, because they had no way to test it. And that problem is this. Stars that are too massive, stars with helium cores weighing between roughly 40 and 130 times the mass of our sun, do not follow this rule. They do something completely different when they die. Something that our physics predicts with absolute certainty, but that we have never been able to directly confirm. These massive stars get so hot in their cores that they start converting pure energy into matter. Gamma rays spontaneously produce pairs of electrons and positrons, particles of matter and antimatter, created from nothing but heat and light. And when that happens, something catastrophic follows. The radiation pressure that has been holding the star up from the inside suddenly drops. The star loses its balance. Gravity starts winning faster than it should. The core begins to collapse, but then the collapse triggers a thermonuclear runaway. Oxygen, igniting in a flash so powerful it doesn't just kill the star, it obliterates it completely. Not a neutron star left behind, not a black hole, not even a cloud of gas that slowly gathers itself back together. Just an explosion so total and so violent that every atom of that star is flung outward at velocities that escape the gravitational pull entirely. The star destroys itself so completely that nothing remains. This is called a pair instability supernova, and the physics predicts that any star in that mass range will end this way, which means that no single star in that mass range should ever leave behind a black hole. Stars above 40 solar masses collapse into black holes before the pair instability kicks in. Stars above 130 solar masses are so heavy that even the pair instability can't blow them apart. They collapse straight through into a black hole. But everything in between, the 40 to 130 solar mass range, gets completely annihilated. No remnant, no black hole, a gap. This predicted gap has been sitting in the textbooks since the 1960s. For 60 years, physicists believed it was real, but couldn't prove it. They had no way to map the masses of black holes across the universe in enough detail to see whether the gap actually existed. Until gravitational waves. When LIGO made its first detection in September 2015, it wasn't just a scientific achievement, It was the beginning of a completely new kind of astronomy. For the first time in history, we could detect objects that emit no light at all. Not black holes by watching them pull on nearby stars. Not black holes by seeing gas heat up as it falls in. Black holes by feeling the ripples they make in space itself when they collide. And crucially, we could measure exactly how massive those black holes were. The first detection in 2015 revealed a merger that produced a final black hole about 62 times the mass of the Sun. Extraordinary on its own. Then the detections started coming more frequently as the instruments were upgraded and made more sensitive. By the time the fourth observing run completed and the fifth catalog was released in May 2026, the total had climbed to 390 detected events. And with 390 data points, for the first time, you can start doing population science. You can start asking not just what is this black hole, but what is the distribution of all black holes, and is there a gap? A team led by Hui Tong, a PhD researcher at Monash University in Australia, working with the ARC Center of Excellence for Gravitational Wave Discovery, did exactly that. They analyzed the mass distribution of all the black holes detected in LIGO, Virgo, and CAGRA's fourth catalog. They were looking for the gap, and they found it. A distinct, statistically significant absence of black holes in the secondary mass, the smaller of the two merging objects, between approximately 44 and 116 solar masses. 44 to 116 solar masses. The forbidden zone, empty, exactly where pair instability physics said it should be empty. Professor Eric Thrain, chief investigator at the Oz Gravitational Wave Research Center, put it this way: we are seeing indirect evidence of one of the most titanic blasts in the cosmos. Pair instability supernovae. Stars dying so violently that they destroy themselves completely and leave nothing behind. Events so powerful that they have been removing an entire category of black holes from existence for billions of years. The gap is real. The forbidden zone is confirmed. But here is where it gets truly unsettling. Because some of the black holes in the catalog are sitting inside the forbidden zone, not below it, not above it, inside it. How? If single stars cannot produce black holes in the 50 to 130 solar mass range, what are these objects? Where did they come from? The answer that the data is pointing to is something that sounds more like science fiction than astrophysics. These are second-generation black holes. Black holes that were not born from dying stars at all. Black holes that formed by two smaller black holes, born directly from stellar collapse below the forbidden zone, finding each other, orbiting each other, and eventually spiraling together and merging. The product of that merger is a black hole bigger than either parent. And if that product lands in the mass range where no single star could have created it, it can only be explained as a black hole that has already merged once before. Two signals in the catalog are particularly striking. GW24STONE0011, detected in October 2024, and GW241110, detected in November 2024, detected just 1 month apart. Scientists analyzing these signals say the black holes involved in both events show signs of being second-generation objects, products of earlier mergers, black holes with a history, black holes that have already survived one cosmic collision before participating in the one we detected. Think about what this means. We are detecting black holes that have already been through a merger. We are watching hierarchical black hole growth in real time. A small black hole forms from a dying star. It merges with another small black hole. The result, now larger, now in the forbidden zone, eventually finds another partner and merges again. We catch that second collision, and in the data, we can see the fingerprints of its past. And then there is GW231123. GW231123 deserves its own discussion. Detected on November 23rd, 2023, this single event is described by the LIGO Virgo CAGRA collaboration as, and I am quoting directly, a real challenge to our understanding of black hole formation. The two black holes that merged were approximately 100 and 140 times the mass of our Sun. The result was a single black hole more than 225 times the mass of our Sun. 225 solar masses. The most massive black hole merger ever detected through gravitational waves. Both of the original black holes, 100 solar masses and 140 solar masses, were sitting inside or just above the forbidden zone. They cannot have formed from single stars. They are second-generation objects, or possibly third-generation, black holes that have been growing through successive mergers over cosmic timescales before we finally caught them in their last collision. Professor Mark Hannum of Cardiff University said this about GW231123. This presents a real challenge to our understanding of black hole formation. Black holes this massive are forbidden through standard stellar evolution models. Forbidden, the word the scientists themselves are using. But the catalog did not stop at the forbidden zone revelation, because inside the same release, there was a second discovery that may be even more profound. On January 14th, 2025, the detectors picked up a signal designated GW25014, and this signal was different from everything that had come before. The signal-to-noise ratio, the measure of how clearly the signal stood out from background noise, was 76.9. The previous record was considerably lower. GW25014 was the clearest, cleanest, most perfectly resolved gravitational wave signal ever detected, clear enough that scientists could do something they had never been able to do before. They could listen to a black hole ringing. When two black holes merge, the resulting object is not immediately stable. It vibrates, it oscillates, it rings, like a bell that has just been struck, gradually settling into its final shape as it releases the last of its excess energy as gravitational waves. This is called ringdown. Physicists have been predicting for decades that they should be able to measure this ringing and use it to test Einstein's general theory of relativity in extreme conditions, to check whether the equations hold when space-time itself is being violently distorted. With GW25014, for the first time in history, they measured 3 separate vibrational modes from the ringing black hole, 3 distinct tones in the gravitational wave signal, each corresponding to a different mode of oscillation in the newly formed black hole. And all 3 matched the predictions of general relativity to extraordinary precision. Dr. John Veitch from the University of Glasgow described it this way. With the clarity of the signal, we were able to compare the warped space-time before and after the black holes merged and confirm that the total area of the event horizons increased after the merger, exactly as Stephen Hawking's black hole area theorem predicts. Stephen Hawking's area theorem, published in 1971. Confirmed in the gravitational wave data from a collision that happened more than 1 billion light-years from Earth, whose signal reached our instruments on January 14, 2025, one of the most precise tests of general relativity ever conducted. And it passed. Einstein's equations held even in one of the most violent environments the universe can produce. But think about what that means on the other side. Those equations, the same equations that just passed the most stringent test ever applied, are also the equations that predict the forbidden zone. The same physics that is now confirmed to extraordinary precision is the same physics that says the second-generation black holes we're detecting should not be able to form from single stars. The theory is right. The gap is real. And something is making black holes inside the gap anyway. Something is happening in the universe that creates these objects through a pathway we are only beginning to understand. The scale of what has changed in 11 years deserves a moment. In September 2015, when LIGO made its very first detection of gravitational waves, the scientific community was stunned. A century after Einstein predicted that ripples in space-time should exist, we had finally detected one. One event, one signal. One brief chirp lasting a fraction of a second as 2 black holes merged 1.3 billion light-years away. Scientists spent months verifying that the signal was real before announcing it to the world. Today, in June 2026, the detectors pick up 3 to 4 gravitational wave signals every single week. Every week. The phenomenon that earned the scientists who built LIGO the Nobel Prize in 2017 is now a routine occurrence. What was once a once-in-a-century confirmation of Einstein's theory is now happening on a Tuesday afternoon. And each of those signals is a window into a black hole merger that happens somewhere in the universe between millions and billions of years ago, whose ripples have been traveling across the cosmos ever since and just happened to wash past Earth this week. 3 to 4 events per week, and the detectors are getting more sensitive. The collaboration has already described plans to continue upgrading the instruments, increasing their reach deeper and deeper into the observable universe. The number of detections will continue climbing. Think about what 390 events means for science. In 2015, we had 0 directly measured black hole masses, 0 direct data on how massive the stellar origin black holes actually are in the real universe, as opposed to what our models predicted. 1 event gave us 1 data point, 10 events gave us 10. 50 events started giving us statistical population data, but 390 events gives us enough to start doing the kind of analysis that Huitong and the Monish team did, mapping the mass distribution of black holes across the cosmos and finding the forbidden zone, finding the gap that pair instability physics predicted 60 years ago, and that we only just confirmed now. And 390 events is not where this ends. A 5th-generation detector called Einstein Telescope is in development in Europe. A planned detector called Cosmic Explorer in the United States would be 10 times longer than LIGO's current 4-kilometer arms. These next-generation instruments would be sensitive enough to detect every black hole merger in the observable universe. Every single one. Not a sample, not a subset. All of them. The map of black hole masses that Huitong's team started drawing with 390 events would be filled in with potentially millions of data points. What we know about black holes in 2026 compared to what we knew in 2015 is the difference between having heard of a place and having lived there for a decade. We have gone from theoretical predictions and circumstantial evidence to a catalog of nearly 400 confirmed events, forbidden zone discoveries, second-generation black holes, the clearest test of general relativity ever performed, and the first time we have ever heard a newly formed black hole ring. And yet, the questions pile up faster than the answers. If second-generation black holes exist, if black holes can grow by merging with other black holes and eventually reach masses in the forbidden zone, what is the upper limit? Can this process continue indefinitely? Could there be third-generation black holes sitting somewhere in mass ranges we haven't even mapped yet? Fourth generation? The detectors are not sensitive enough yet to reliably detect the most massive mergers at the greatest distances. GW 3123, with its 225 solar mass product, was at the very edge of current capability. What else is happening out there that we simply aren't powerful enough to hear yet? And the second-generation black holes raise a deeper question. Where do these repeated mergers happen? Two black holes merging once is already statistically challenging. They need to find each other in the vast emptiness of space, somehow end up in orbit around each other, and then slowly spiral together over millions of years as gravitational waves drain their orbital energy. For a second-generation black hole to undergo another merger, the product of the first collision has to encounter yet another black hole. In the average region of space, the density of black holes is far too low for this to happen reliably. Scientists are pointing to specific environments where repeated mergers could occur. Dense stellar clusters, regions where thousands or millions of stars are packed closely together, where black holes are concentrated, where gravitational interactions between objects are frequent enough that repeated close encounters and captures are possible. The centers of galaxies, where supermassive black holes dominate and where dense populations of stellar mass black holes may congregate. Active galactic nuclei, galaxies with furiously bright gas-feeding central black holes, where conditions might allow repeated black hole encounters on timescales short enough to produce the kind of hierarchical growth we are now seeing in the data. We are beginning to map not just the black holes, but the environments that produce them. The detections in the fifth catalog are not just revealing what black holes exist. They are revealing where black holes grow. They are showing us the cosmic neighborhoods in which the rules of physics are being pushed to their most extreme limits. Here is where we stand in June 2026. We have 390 confirmed gravitational wave events. We have confirmed the existence of a forbidden zone in black hole masses that stars cannot create, and found black holes inside it anyway, built from the ruins of earlier collisions. We have heard a black hole ringing after its birth, and measured its tones with enough precision to confirm Stephen Hawking's theorems and Einstein's equations in the most extreme physical conditions we have ever tested them in. We have watched what appears to be a 225 solar mass black hole form from two objects that physics said should not exist as single stellar remnants, and the detectors are getting more sensitive. More signals are coming. The catalog will grow. The map will fill in. The forbidden zone will become better defined. The second-generation black holes will accumulate in the data until their formation pathways become clear. 11 years ago, the universe was silent to us in this way. We could not hear the collisions. We could not measure the masses. We could not confirm the theories that physicists had been arguing about since the 1960s. Now we hear 4 collisions a week, and the sound is getting louder. The universe is not finished with its surprises. Black holes that form inside forbidden zones are already telling us that the story of how the most extreme objects in existence come to be is more complex and more violent and more hierarchical than our models imagined. What else is waiting inside the next 161 detections? What does the next catalog reveal? The instruments are running, the signals are arriving, the answers are on their way. If you have made it this far, you are exactly the kind of person who should be subscribed to this channel, because this is what we do here. No hype, no fake claims, just the real science, explained the way it deserves to be, with the urgency and the weight that discoveries like this actually carry. The universe is doing extraordinary things right now, and most people have no idea. Every week, the detectors pick up another collision. Every paper that comes out of this data pushes our understanding further. Hit subscribe right now so you don't miss what comes next, because the next catalog is already being assembled. The signals from this observing run are already being processed. And when the next major result drops, the next forbidden zone, the next record-breaking merger, the next test of Einstein that either passes or finally breaks, you will be the first to know. Subscribe, hit the notification bell, and stay with us. Because in the history of human science, there have been very few moments where we are genuinely hearing the universe speak for the first time. We are in one of those moments right now, and it is only getting louder.